Robot learning asks a direct question. Instead of programming every movement, can a machine improve from experience? Reinforcement learning, or RL, gives the robot an objective, lets it take actions, observes the result, and updates behavior toward higher reward. It is powerful because many useful skills are too complex to specify as a long list of rules. An RL loop has an environment, an observation, an action, a policy, a reward, and an update rule. The policy maps what the robot senses to what it should do. The environment returns a new state and reward. Over many episodes, the algorithm adjusts the policy to collect more reward. Exploration discovers possibilities. Evaluation checks whether the learned behavior is reliably useful. Observations may include camera features, joint angles, contact forces, or a world model state. Actions may be torques, target poses, or high-level commands. Rewards encode what success means, such as forward speed, stable balance, energy efficiency, or a successful grasp. Value functions estimate long-term return. Policy optimization turns those signals into behavior. Reward design is therefore an engineering decision, not an afterthought. Consider a legged robot learning to walk. It receives body orientation, joint positions, foot contacts, and velocity. It commands joint targets or torques. Reward encourages forward progress, upright posture, smooth motion, and low energy use, while penalties discourage falling and violent impacts. Early attempts look chaotic. With enough varied trials, the policy discovers coordinated stepping patterns no human explicitly scripted. Pure exploration is dangerous on expensive hardware. A robot cannot simply try every torque and learn from a broken gearbox. Teams constrain action ranges, use safety filters, start from demonstrations, and learn mostly in simulation. The hard challenge is to preserve enough exploration for improvement while preventing the learner from exploiting loopholes, unsafe shortcuts, or accidental quirks in the reward. Simulation makes robot learning practical by running thousands of environments in parallel. A walking policy can experience different slopes, pushes, masses, and friction coefficients overnight without wearing out a single motor. Synthetic camera scenes expand visual diversity. Physics is imperfect, but the amount of structured practice is transformative. Real-world testing then becomes validation and adaptation, not the only source of experience. Domain randomization deliberately changes textures, lighting, camera placement, object shapes, and sensor noise during simulation. A policy that only succeeds in one pristine virtual room is brittle. By seeing many plausible worlds, it learns features that transfer better. The goal is not to recreate every real detail perfectly. It is to prevent the learner from relying on irrelevant details that will disappear after deployment. Dynamics randomization applies the same idea to mass, friction, motor strength, latency, compliance, and contact behavior. These properties are difficult to measure exactly and can change as a robot ages or carries a load. Training across ranges makes the policy less surprised by reality. It is a disciplined way to turn model uncertainty from a deployment failure into a training condition. Sim-to-real transfer rarely ends with one export button. Teams fine-tune on carefully collected real data, calibrate sensors and dynamics, and sometimes allow bounded online adaptation. They monitor confidence, intervention rate, and failure modes as the policy encounters the real world. The safest transition starts with conservative tasks and expands capability only after evidence shows that performance survives outside the simulator. Imitation learning uses demonstrations from teleoperation, motion capture, or expert trajectories. Instead of discovering every behavior through trial and error, the robot first learns to copy competent examples. RL can then refine the policy for robustness or efficiency. This combination is valuable for manipulation, where a human can demonstrate what a sensible grasp or handoff looks like long before a reward signal alone would find it. Industry uses robot learning across legged mobility, warehouse picking, autonomous driving, drone flight, and humanoid manipulation. Boston Dynamics develops dynamic mobility. Agility focuses on useful warehouse work. Figure is pursuing general-purpose humanoid skills. NVIDIA provides simulation and training infrastructure. The common pattern is data, simulation, learning, verification, and carefully bounded deployment rather than a single magical model. Different RL algorithms trade data efficiency, stability, and exploration. Value-based methods learn which actions are promising. Policy gradient methods directly improve a parameterized policy. Actor-critic methods combine both ideas. Robot teams choose based on action space, simulator throughput, safety constraints, and whether they can reuse logged data. There is no universal algorithm that removes the need for careful evaluation. This matters because physical environments punish assumptions that go untested. Engineers validate this capability across varied conditions, measure confidence as well as average success, and retain clear fallback behavior. The lesson is practical. A robot earns autonomy by making its assumptions visible, checking them against fresh evidence, and choosing a safer response whenever the evidence is weak. Robot learning turns repeated experience into better action. RL defines an objective and improves a policy through feedback. Simulation supplies scale, randomization prepares for variation, sim-to-real methods close the gap, and imitation adds human expertise. The most capable systems still pair learning with perception, world models, planners, controllers, and safety constraints. Learning makes that whole stack more adaptive. Offline reinforcement learning trains from previously collected demonstrations, logs, and trajectories without taking new risky actions during every update. This is valuable when real-world trials are costly or constrained. The challenge is distribution shift. A policy must avoid becoming overconfident about actions poorly represented in the data. Conservative objectives and validation are essential. This matters because physical environments punish assumptions that go untested. Engineers validate this capability across varied conditions, measure confidence as well as average success, and retain clear fallback behavior. The lesson is practical. A robot earns autonomy by making its assumptions visible, checking them against fresh evidence, and choosing a safer response whenever the evidence is weak. A learner optimizes the reward it receives, not the intent hidden in a designer's mind. If a walking reward misses stability, the robot may discover hopping tricks. If a grasp reward misses object integrity, it may squeeze too hard. Teams use multiple terms, constraints, demonstrations, adversarial tests, and video review to catch loopholes before they reach hardware. This matters because physical environments punish assumptions that go untested. Engineers validate this capability across varied conditions, measure confidence as well as average success, and retain clear fallback behavior. The lesson is practical. A robot earns autonomy by making its assumptions visible, checking them against fresh evidence, and choosing a safer response whenever the evidence is weak. A learned policy is ready only when it succeeds beyond its training distribution. New objects, altered lighting, changed loads, sensor noise, delayed commands, and unexpected contact. Evaluation should report success, safety interventions, energy use, recovery behavior, and confidence. Generalization is the difference between a compelling lab clip and a reliable physical capability that can earn a place in production. This matters because physical environments punish assumptions that go untested. Engineers validate this capability across varied conditions, measure confidence as well as average success, and retain clear fallback behavior. The lesson is practical. A robot earns autonomy by making its assumptions visible, checking them against fresh evidence, and choosing a safer response whenever the evidence is weak. The standard for responsible robot learning is not whether the policy can produce a spectacular success once. It is whether teams understand its objective, training distribution, uncertainty, failure modes, and safe operating boundary. With that discipline, learned behavior becomes a valuable capability instead of an opaque gamble with real people and machines.